Okay, good evening. So I'll get started. I welcome the viewers to this problem solving and live interaction session for the subject strength of materials. Today we'll be discussing the contents of week 10, which has to do with unsymmetrical bending as well as some rudiments of displacement, deflections, beam deflections. So before we start, are there any questions? I'm sorry that I had to push the session 2 days farther because I was not fully well. In fact, I still am not fully recovered. So in case there is any lapse in the delivery, I request you to bear with it. But in the meantime, are there any questions about what we discussed previously? If there are any, I'm happy to take them now, or we can also take them as we proceed. So if there aren't any, so yeah, yes, please.
No, sir.
Okay, okay, thank you. All right.
Your health is good now, sir?
Yeah, I'm fine. Yeah, thank you for asking. All right. So we'll get started. So I'll just briefly introduce myself quickly. My name is Ganesh Ramaswamy. I'm a PhD scholar in the Department of Applied Mechanics and Biomedical Engineering, working under the guidance of Professor K. Ramesh and Professor U. Saravanan. So let us look at the first question of the day. The flexural rigidity of a beam subjected to bending is what? The amount of deflection a beam undergoes under the load, the amount of bending stress a beam can withstand without failure, the ability of the beam to resist bending under the load, the ability of the beam to resist twist under the load. So this comes from our moment curvature relation, which we will see a while later. So any quantity, basically stiffness, rigidity, these are all measures of how any object resists its deformation. So when it comes to an axial member, let us say, so I have an axial pull like this. So we know that the change in length is, let me call this P, and let the actual length be A, L and A, and area be A and so on. So this is PL by AE. So P by delta L is AE by L. So this is its axial stiffness. Similarly, this is the member's axial stiffness, this quantity. Similarly, when it comes to bending of a beam, in fact, I can take this itself. When it comes to bending of a beam, call this some moment, and this would have, I'll just roughly draw it in an exaggerated scale. So let us say that it is having some theta. So what is the uh, moment required to generate a unit rotation, if we see? So it will come as some relation of its moment of inertia which has to do with the geometry. Then we will have Young's modulus, which is where the material comes in. Then again the length will also come because it will be the bending stiffness. Now if we were to separate out the length from the bending stiffness, we will have the flexural rigidity. That is at a section, at a cut section. If I were to look at this beam, let us say it is a rectangular beam, and made of some material and of some dimensions BD something, and let this be some steel. So EI is what we term as its flexural rigidity. Flex meaning bending, so flexural rigidity. So from the name as it suggests, if we were to increase the flexural rigidity, how? We can increase it in multiple ways. We can either make the material more stronger, some stronger alloy or something like that. Or we can increase B and D, the dimensions of the beam, keeping the material same. Now again, since we know if this is Y and this is Z, and IZZ resist the bending in this case, if we were to take, then naturally we will see that increasing B will only result in a linear change in the flexural rigidity. Whereas if we were to increase the depth, it will lead to an exponential change in the uh, in IZZ and consequently flexural rigidity. So in that case, we consider that this is the ability of the beam to resist the bending under load. And a slight change in depth or in the material parameter will bring its stiffness, will increase its stiffness and consequently reduce its deflection. So I hope that is clear. If the flexural rigidity of the beam, oh, that is what is asked next actually. Okay, let me copy and take this here. If the flexural rigidity of the beam is increased, keeping the load and the length of the beam constant. So the load is constant that is applied on this beam. The length is constant, so there is no change in the
the deflection will decrease, sir.
Yeah, exactly. So if this were to increase, we know that deflection is represented by V is proportional to so if this were to increase, then naturally our deflection will decrease. All right. So the equation EI d4V by dx power 4 equal to W for a homogeneous slender beam whose axis aligned with the x direction is applicable for which of these cases? E is the Young's modulus, I is the moment of inertia, V is the deflection, and W is the load applied. So what we are saying is we have some loaded beam like that. This is a UDL. You can just assume that to be a UDL. Some units, some load. So it says EI d4V by dx power 4 is equal to W. So what is special about this equation is this comes, this is a fourth order equation. So we will need four constants in order to determine the deflection accurately at any point. A closed form expression for the deflection would require integrating this expression four times, which will need four constants. So those four constants we will have to supply from the physics of the problem. In such a case, what can those four constants be in this problem? It's a symmetric problem. And let us say that it deflects something like that. Let the deflected shape be something like that. I'm not accounting for the movement of the slight movement of the roller. Even if that were to be the case, it will still be symmetric. So if this is the elastic curve. Elastic curve meaning the deflected shape of the beam. Now we know that here we have def deflection. Let this be A, B. We have deflection at A is 0. Deflection at B is 0. Now slope at A is not 0. But something being not 0 is not much helpful to us. At this point, at the midpoint, however, we can see that if I were to draw a tangent, I can see slope at the midpoint is 0. At the same time, my deflection at the midpoint, by virtue of the problem being symmetric, is maximum. So V at midpoint is V max. So these are the boundary conditions which I can apply. Once I integrate this equation, I can systematically apply them, and I can arrive at what the deflected curve is. Now, in addition to this being a statically determinate problem, if we were to apply this to a statically indeterminate problem, in general, statically indeterminate problems, we do not have expressions for the reaction upfront. So we do not know no reactions upfront. So what happens is we will not be able to write the actual expression for the bending moment at any section, independent of the reactions. That is, we will only be able to fill in the symbols for the reactions, but we will not be able to determine the reactions completely. In such case, if we were to use the second order equation, which relates the bending moment and the curvature, which is what we generally do, in such a case, this already bears one unknown, or maybe more than one. Because of the virtue of the problem being statically indeterminate, we do not know the reactions. However, we do know the load. No matter what the problem is, statically determinate or indeterminate, we'll definitely know the load. So if we were to approach it using the fourth order equation instead of the second order equation, this becomes useful in solving problems where the reactions are not known. So there is no need for you to calculate the bending moment upfront. You can directly approach from the load, with the only catch that you have to integrate it 4 times. So you should be able to supply 4 boundary conditions that are useful and meaningful for you to get the solutions. So this is generally used in plates, but that is something I'm just mentioning. It comes in a course called Plates and Shells. There we will be using that extensively. So these are useful for both statically determinate as well as statically indeterminate problems, the fourth order equation. Whereas for statically determinate problems, one may well use the second order equation, this one, integrate it twice in order to get the slope, the deflection. I hope that is clear. Okay, so identify the nature of bending stress variation along the depth of the beam shown. So actually this is an experimental image. So what they have done, they have actually created an epoxy model of this hook. They held it in one end and they have loaded it here. And there is something called stress freezing that is done, where it is put in a furnace in a loaded condition, and it is soaked for a certain period of time under a specific thermal cycle. And once that is removed, the loads get the stresses get frozen into the model. Then subsequently we can take it out, cut it, view it in a polariscope, and so on. So this is the loaded stress frozen model of a hook, and we can see that this is actually, this does take bending. It is clamped here, or rather this is where it was hung. So here translation is arrested, rotation is not arrested, fine, and I load it here. So I can see that this portion actually undergoes bending because of the load. Now we also saw in the lectures of photoelasticity that for a beam subjected to pure bending, we had our fringe order 0 pass at the center, and then the first fringe order came in here, and second, and so on, depending on the load. But one thing we saw that it was equidistant from the center, which is because we saw sigma 1 is nothing but m by I into y. That is some constant c into y. So it has a linear variation across the depth. As I increase y, my stress varies linearly, which is something we have seen, that under the action of this, my stress variation will be linear like this. It will just be a triangle. Whereas here, if we were to see, we can see that this blue band does not fall at the exact center of this cross section. There is a 0th fringe order, and then towards one side, the fringes are more concentrated. Towards the other side, the fringes are more spaced out. So this tells us something, that this actually is not a linear variation. So it is not constant, it is not linear. If this was parabolic, it will not be equidistant, but at least there will be some semblance of symmetry about the neutral axis, which is also not there. So the only conclusion that can be drawn is that it is hyperbolic, which it indeed is actually. And this is called an initially curved beam. Such sections are not analyzed in the present course. It might come in the higher level courses, but nonetheless, this is something interesting to know, that once we have a beam, it is not that always load makes things nonlinear. Even the geometry of the body to up to on which we are applying the load, if it has an initial curvature, then there will be second order effects that will set in, which will make the problem more complex. So in an initially curved beam, the bending stress variation is actually hyperbolic. So I hope. Yeah, yes, please.
Just so is this true only for this hook, or for any curved beam would the
No,
variation
generally
always be
any
hyperbolic?
curved beam, if you see, if there's an initially curved beam over which you are applying a load, there is some specific name also to dedicated to the scientist who actually worked out the mathematics to show that it comes out to be hyperbolic.
Right. Right. And does the direction of load application with respect to the curvature actually matter? So here, for example, I assume the load is applied
Yes.
downwards, but what if I applied it upwards? Would it still follow the same? I mean, obviously the pattern would be the same,
Yeah.
but would it still be hyperbolic?
I don't see why not actually, because it has to be objective that way. Because even in our derivations, if we were to flip the moments, only the nature of the stresses between these should flip. But it's an interesting thought. I'll maybe look into that. But I don't see any reason why it should change.
Sure.
Yeah. Actually speaking, this is getting bent like this presently. If I were to bend it this way, so maybe value-wise there could be differences, but in principle the variation should still be hyperbolic. Is my thinking.
Right. No, the only reason I was wondering is
Yeah.
because you would basically be bending into an arc.
Okay.
when you apply a moment in the opposite
All
direction.
right.
So that's the only reason I was wondering. That's all.
Okay, okay. Okay. Well, let me give it some thought and get back to you.
Sure.
All right. So this is the case of an initially straight beam. In the case of an initially curved beam, it'll be hyperbolic. All right. So let us look at this question. The magnitude of the maximum deflection of a cantilever for a cantilever, as shown in the figure, subjected to a moment m at the free end, is given by what? L is the length, E is the Young's modulus, I is the moment of inertia. So, okay. So let us try to solve this using in fact, I'll derive the rudiments of this curvature equation a little later. Let us say for this beam, I have the moment this way, and I have the fixed end here. So my bending moment diagram is nothing but it is just a rectangle. Shear force diagram is non-existent. So this is the SFD, which is 0. So the bending moment is, if I take my sign convention, with this sign convention, if I cut a section here, I will have to put a moment like that, which will balance out M, which means this is my bending moment diagram for this problem. Now, if we were to use our moment area method, in this case, what will we generally do? We'll take this here, and then we will integrate it 2 times. Integration is nothing but the evaluation of area under some curve. So that curve happens to be m by ei. So m I already have. If I just scale it by a factor of ei, because in this problem ei is constant, it is not having any variation, so it will just result in a smaller rectangle with a lesser height, that is all. So I'll just remove this, and this will be m by ei zz. So this diagram I have. Now it is just a matter of I was doing the integration like that. Now I can do it from the figure itself because of the simple geometry of the diagram, m by ei diagram. We can easily calculate the area between 2 points and evaluate slopes and deflections. So using the moment area method. So what does this say? That if there is an elastic curve like that, and this is my axis, so the slope between any 2 points is given by the area between those 2 points area of the M by EI diagram between those 2 points. So if I were to say, call this A and call this B. So theta B minus theta A is the area of this MB by EIZZ diagram between these 2 points, between B and A. So therefore theta B minus theta A is the area of this. If this is L, it is nothing but MB by EIZZ into L. Now from the problem, I know that for the fixed end, my slope is 0. So theta A is actually 0 for this problem. So therefore, this directly gives me theta B is ML by EIZZ. I'm writing MB. When we actually read out the value of MB, it will come out to be M, which is applied. So that will be, so we may well drop that superscript there. So this is ML by EIZZ. So we have the slope at the free end. Free end of the loaded cantilever. Now for the deflection, using the moment area method, so basically what the deflection gives us is, if there is the elastic curve is like that, and if we take 2 points, and if I draw tangents at those 2 points, the difference between the how do I put this? The difference between the deflection of those 2 points is what the tangential deviation is. Let us say if I draw one over here, if this I take it as 1 point and this I take it as the other, uh, yeah, it is still the intersection. Okay. So this difference is given by, this is known as the tangential deviation between 2 points on the elastic curve. And this is given by the first moment of area of M by EI diagram. So in this case, T, I have called this A, this B. So TBA is nothing but the area, moment of area, moment of M by EI diagram between A and B about B. So in such a case, TBA in this case happens to be the area of this rectangle is nothing but M by EIZZ into L. This is my area into the centroid of this area is the center of the beam, and I have to take moment about B. So this will be L by 2. So this is L by 2. So therefore TBA is nothing but M L squared by 2EI ZZ. So here we have only calculated the tangential deviation presently. Now if it turns out that you have calculated tangential deviation out of which with respect to with one point as a reference which already has a zero slope. So if this has a zero slope, then this is my tangent over there. So the tangent and the axis with respect to which we are calculating the deflections when it is same, then the value can directly be read out as the deflection at that other point. So by virtue of deflection and slope at A being 0, directly gives us deflection at B, which is ml squared by 2EI. So ml squared by 2EI is how it comes about. Now if we were to do the same thing using our double integration, what would we have had? EI d2E by dx squared would have been equal to m, because my bending moment is m at any section. So therefore d2E by dx square is m by EI, dv by dx is mx by EI plus C1, v is mx squared by 2EI plus C1x plus C2. Now at x equal to 0, my slope, that is dv by dx, is 0. So therefore C1 is 0. At x equal to 0, v is also 0 by virtue of that being a fixed end. Therefore C2 is also 0. So therefore I have my slope equation as dv by dx equaling mx by EI. And my deflection equation equaling mx squared by 2EI. So the advantage of using the double integration method is I get a generic expression for my slope and deflection, using which I can calculate the deflection at any point rather than at specific points. So if I were to do the same thing at some L by 3 using the moment area method, then I will have to recalculate my moments about that point and the area of the M by EI diagram about that point. Whereas double integration method directly gives us one general expression. But during integration, again, if the curve is very simple to find the area, then moment area method is much easier if we get a grasp of that. So therefore, at the free end, x equal to L, my theta at B is nothing but the same dV by dx at x equal to L, which is ml by EI. And the deflection at B is ml squared by EI, 2EI. So which is consistent with our answers what we got previously. So this is a very rudimentary problem just to get a flavor of how to apply the moment area method as well as the double integration method, and what are the advantages of one over the other. Granted, if we had some sinusoidal wave or some random function that describes the load here, then naturally our bending moment diagram is going to be much more complex, and it will no longer be simple shapes. It will be some higher order curve, in which case we can go with our double integration method, which is the basis for everything. The foundational equation is this, that we have related our deflection to our moments. From there on, people have seen how to simplify this for simple cases. So that is how the other methods have come about. So, okay. So I hope that is clear. Now let us look at this question just to identify the boundary conditions. For a beam subjected to a load P as shown in the figure, identify the correct boundary conditions. V is the deflection and theta is the slope. So for this beam, let us say if this was not there, it is just a cantilever with a load somewhere in the span. So it would have deflected like that. But because this is there, so the deflection has to go to 0 here. So this would be somewhat of the deflected shape. And why doesn't it start like that? Because this is a fixed end. So at the fixed end, I have to have 0 slope. So the deflected shape is going to be something like that. So from the problem, we know from the problem's arrangement, we know A being a fixed end, we have slope and deflection at A equaling 0. We have B being a propped end, propped, hinged, whatever. With a hinge. So therefore, deflection at B is 0. So VA equaling 0, theta A not equal to 0. So this is clearly not correct. So this is not a correct option. So VA equal to 0, theta A equal to 0, VB is 0, theta B is non-zero. So this is correct. And what is wrong in this? It says that deflection is non-zero, which is not true. And in the fourth case, it says everything is 0, whereas this is actually not true. So that is why the second is the correct option. So I hope that is clear. Another thing to note here is not a symmetric problem because the boundary conditions are not symmetric. So which is why my deflected shape will not have its maximum dip just underneath the load. That will only happen when it is loaded symmetrically in all respects. That is not only the applied load, even the support conditions would have to be symmetric. So would have to be the material properties and things like that. Only then uh, it will be symmetric and the maximum deflection will come under the load. Whereas this is not the case here. So the deflection would be something like that, which will peak somewhere over here between the load uh, and the support and the prop support. So you can work out and see, just assume some value for P and you can work out and see where it would actually come out to be by taking some particular distance for this. Or if you take this also to be a variable, then you will get a more general expression for that. So I hope that is clear. All right, so let us look at this question. The beam given in the figure is said to undergo unsymmetrical bending if the beam deflects in both x and z direction. So what are we talking about here? So if I were to cut a cross section like that, and for the sake of this example, I'm again assuming this to be a rectangle. Or should I? Let me take this as some generic shape like that. And let this be y, let this be z. So let us say this is how the beam looks when we cut it. Its cross section looks when we cut it. So if the beam deflects in both y and z direction, then naturally there is bending about two axes. So that is unsymmetrical bending. If the bending moment acts in the plane of symmetry, then there won't be any out of plane displacement, out of the plane of the moment that acts, out of the bending plane, actually speaking. So in that case, we will not have unsymmetrical bending. If the moment acts with respect to both y and z directions, naturally there will be a resultant uh, moment which will take it out of plane. So that will also lead to unsymmetrical bending. If the cross section has a plane of symmetry and the end load acts on that plane of symmetry. So let us say that this was a rectangle, and if I were to load it like that at the free end, then naturally it will be having bending only in the xy plane. So there won't be any z component of displacement for the entire beam. So in which case this is not bending unsymmetrically, it will be a symmetrical bending. Symmetrical bending about the xy plane, which is actually cutting, slicing through the center of the beam, which is what we are seeing as a projected longitudinal section. So I take it that is clear. Unsymmetrical bending is actually just an extension or a more general case of our flexure that we have seen so far. So instead of one axis, so far we have been seeing beams like these where we will be having moment that will be parallel to the z-axis with its axis parallel to the z-axis. Now, in addition to that, if I were to have this, then naturally, by virtue of this moment, it will have some deflection, and by virtue of this, it will have some other deflection. both can be linearly superposed for us to get our results in linear elasticity. So in such a case, instead of moving in this plane alone, it will also have movement in this plane. So the net result will be it would have gone somewhere over here or somewhere over there, something to that effect. So that is what is unsymmetrical bending. So the equations, if we see, it will have uh, asymmetry coming in because of either moments that are acting about two axes. So either the section can be symmetric, and by section can be symmetric, I mean the product of inertia is zero. So IYZ, if it is zero, but it is having bending moment in two directions. So this is MB about Z, this is MB about Y. So if a case like this arises where there are two types of bending moments that are getting induced in mutually perpendicular directions, then this would lead to unsymmetrical bending. Or if I were to take this case, which does not have a symmetric section, meaning IYZ, product of inertia, is no longer equal to zero. Why do I say that? Let us say I divide this. These are not equally distributed. So if I were to take the product of inertia, I'm sure all of you are aware of how to take that. So for the first quadrant, whatever area into its centroid, into that portion's centroid, similarly added with this portion into its centroidal distance, which can be resolved into two components, y and z. So a y z, that is what is a y square we saw is izz, dA y squared. Similarly, dA xy or dA yz will actually be Iyz. So when that is not zero, even if I were to have a moment acting only about one direction, I will still have deflection, not strictly following in that direction, but there will be some more inputs to that because of this not being zero. So that also causes unsymmetrical bending. So I hope that is clear. Now, in such a case where there is unsymmetrical bending, our neutral axis will no longer be parallel to our, as we were seeing here in this case, in the earlier cases that we saw, in the absence of this, this would have been my neutral axis where sigma x is zero. This will be in maximum tension, this will be in maximum compression, which when I draw it sideways, it will look something like that. That is what we were seeing. So this was the neutral axis. Now, if I were to, let us say, remove this instead, but apply this, this also becomes a case similar to that, only it is flipped. So this would have been my neutral axis, where this will be maximum tension, this will be maximum compression. Now here, the distribution would have been like this. So that would have been the only difference. Whereas if both were to act simultaneously like this, then my neutral axis will have some generic orientation. And in problems, it is worthwhile to know where the stresses will peak. So let us say that if my neutral axis is this way, we know that our bending stress is maximum at the farthest fiber from the neutral axis. So if this is the farthest, we will have maximum bending compression and maximum bending tension there also, depending on the nature of the bending moment that has been applied. So for that case, we may have to plug in the coordinates y, z, both the coordinates into the equation in order for us to calculate the net stress, which includes the effect of MBY and MBZ. So in such a case, first let us try to identify how to, let us try to understand how to actually find out where the neutral axis position will be. So a cantilever beam with a circular cross section is subjected to two end moments of equal magnitudes as shown. So the YZ plane, we have a circle and it is applied with two moments like this. So in fact, let me just so I have the moments acting like that, and the question asks the correct depiction of the neutral plane, neutral axis, wherever my the axial stress, normal stress, not the axial stress, normal stress because of the bending, where does it go to zero is what is asked. Now, if I were to disregard this for the time being and just look at this moment, so what will happen actually? In fact, I can draw this again. When I have this, if I were to wrap my fingers around this arrow, double-headed arrow, such that my thumb points in the direction of the arrow, then I can see that it will create a bending which will result in tension on this side. It will divide it into two zones where this will be in tension and this will be in compression. So I hope you are able to see that easily. Now, if I were to take this as the case, the other moment, if I were to apply individually, then naturally this will divide into two zones, which will cause this to be in tension and this to be in compression. Now the idea is just to superimpose these two. If I take this here and then I superimpose this with that, granted it is not coming very clearly, so what we can do, we can just, I'll highlight the tension portion with this color and compression with blue. So the sum total of these two, when put together, I can see that just a moment. So which is the area that is in tension that is common in both the places? That is what we need to look out for. So if we see this portion is in compression in both the cases and this portion is in tension in both the cases. So at the other quadrant, naturally one is causing tension and the other is causing compression. So when both get superimposed, at some point, at some points it will get nullified, right? Because one is negative and one is positive. So in one of the quadrants, if these values are getting added to one another, so along certain points, they will nullify each other. So naturally, my neutral plane has to pass through that, pass like that. So I hope that is clear. If it is not clear, you may please ask and I'll be able to explain this again. In fact, you'll be better off dividing this into 4 quadrants because circle generally it is easier to find out. Whereas, or we will also do one example for a rectangle on how to find out the neutral plane. Then it will be much more clearer. So therefore, the final neutral plane would actually be something like that. So this is my neutral plane. If I were to take a rectangular section and subject it to movement like that, let these be the moments that are getting applied. So for first these two, if I take, for this, I will divide this section into 4 quadrants, let us say. So in this case, this load causes tension here and compression here. So that is clear. Similarly, if I take these, this plus this plus, and I again divide them into 4 quadrants. So this will cause tension here, tension and compression. Now when we superimpose these two, you just have to see which are the quadrants where both are causing tension and which are the components where one is nullifying the other. So here we can see one is causing tension, one is causing compression. So naturally there will be some points which will go to 0 here. Positive and negative will add up to 0, which means there will be points which will have experience sigma x equal to 0, which is what our definition of a neutral axis is. So it will be something like this. The neutral axis will pass through something like that. If the neutral axis is here, the maximum tension will be at this point because this is the tension end. The maximum compression will be at this point because this is the compressive side of the neutral axis. So I hope this example gave you a little bit general idea about how to figure out which is the tension and compression side in the case of unsymmetrical bending. And yeah, this is subjected to both actually. I should put the loading also. Yeah. So, all right. If the axis of the beam is aligned along x, the neutral axis of the beam will be along the axis passing through the centroid of the beam, along the outermost or bottommost part of the beam, along the axis where sigma x is equal to 0, along the axis where sigma y is equal to 0. Now we are talking about a beam which has its axis along x. So all these tension, compression, whatever we are seeing, these are all stresses in with the subscript x, assuming that x is the longer dimension of the beam, which is the length of the beam. So x is the axis. So along the axis, whatever is the normal stress by virtue of bending, that is what we are trying to study here. So wherever that goes to 0, we define that as the neutral axis. So I suppose that is what we have been seeing here. I'll just put one line dotted so that yeah. So this is my N. Okay. Okay, so let us look at this question. Considering that a steel section of Young's modulus so much and a rectangular cross section as shown is used as the beam in the figure shown. So we have the figure like this. It's a cantilever beam where we have our load acting at the center of the beam, which is at 5-meter distance. Report the magnitude of slopes represented in theta into 10 power 4 radians and deflection in mm at the points for each of the case of arrangements. So how many arrangements to, okay, we presently have only one arrangement. For this arrangement, at different points, we have been asked the quantities, slope and deflections and so on. So let us see how to go about doing that. So if we were to approach this using our double integration method, so we have EI d2v by dx squared is equal to the moment. Now, in this portion of the beam, the bending moment is actually 0. So we may well avoid it in our calculation totally. So what we generally, we will have the bending moment diagram like this for that case. So or rather, instead of solving using the double integration method, let us apply the moment area method again and try to do this. So I have the load applied here. This is P, which is some 5 kilonewton. So the bending moment diagram for this case is like that. So this is 5 into 5. This is 25 kilonewton meter. Or rather, first let me put everything in terms of symbol so that it doesn't become very messy. So let this be L, let this be L by 2, and let that be P. So this is PL by 2. So I have the bending moment diagram here. Okay. Now, first the question asks, what is the value of theta A? So this we don't need to do any analysis in order to find this out. A is a fixed n. Therefore, theta A is 0. theta B, theta C is asked. So which is B and C? So the free end is B, this is C, and this is A. So therefore, theta C minus theta A is area of M by EI diagram between C and A. So theta C minus 0, because theta A is 0, is nothing but M by EI. So what is the area of this? It is half into M is PL by 2 into L by 2 whole by EI. So this comes out to be theta C is PL squared by 8 EI. So this much we have got. Now similarly, if we were to take the points as theta B minus theta A, we will still land up with the same answer. That is because there is no contribution of moment in this portion of the beam. So this tells us something interesting, that once we have the deflected shape like that, after the load is applied, this portion just remains straight. So this portion just undergoes rigid body movement, rigid body rotation about the point C. So the slope remains the same. If this is straight, no matter where I draw the tangent, its slope with respect to the horizontal is going to be the same. So that is what this implies. And this is also shown in one of the lectures. Professor has shown that using the example of a cantilever beam where it is loaded somewhere midway and the remaining portion remains straight, although it has rotated. It has not bent, it has just simply undergone rigid body rotation. So is also equal to the same thing. So this gives theta B is also equal to this quantity. So theta A, theta B, theta C is done. Now we just need to find out the deflection at point C. Yes, please. Yeah.
Sorry, I'm not sure if it is just me, but the screen seems to be
Oh, is it?
um, hasn't gone
Okay,
to wherever
just
you're
one moment.
writing. Sorry. Okay.
Oh, just a moment. Yeah. Okay. Thank you, Mr. Jayakrishan, for remarking that, because I was just going on writing. So good thing you stopped me. There was some issue with the internet. Anyway, so theta B is equal to theta C, and we have got this as PL squared by 8EI. So now the next question asks what is the deflection at point C. So let us calculate the deflection at point C. So TCA is nothing but moment of M by EI diagram with respect to C. So this is, but since VA is 0 by virtue of that being a fixed n, therefore TCA is nothing but my deflection at C, which is nothing but area, which is this quantity. So let us evaluate that. So this is the area of this. In this is B, and this is C, this is A. So we see this half PL by 2 into L by 2. This is my area of M diagram divided by EIZZ. So this is the area of some issues there. Okay, so this is the M by EI diagram into the centroid of this will be at a distance of 2/3 the base from this point, which is nothing but 2 by 3 into the base is L by 2. So this is what VC is. So that will be PL cube 2PL cube by 8 8 8 twos are 16 threes are 48 EI CZ, or VC is PL cube by 24 EI ZZ. So for our normal cantilever, we know the very famous expression PL cube by 3 EI. So if I were to plug half, so half cubed is 1 by 8 by 3 is 1 by 24. So which comes out to be correct. So this is just a cross check for us to do. So VC comes out to be PL cube by 24 EI. Very well. And the maximum deflection. Now from this question, we can see that our deflected shape will be like that. That is, it will have curvature and then it will be straight till here. But the maximum deflection is actually this quantity. So which is this plus whatever this quantity is. Now what is the deflection between y BC. What is this quantity? It is nothing but my theta over here into L by 2. So that is what that is. So therefore, deflection at the free end, or deflection is maximum at the free end. So at B is nothing but VC plus theta C into L by 2. So if I were to see this using a diagram, to an exaggerated scale, if I draw this, and of course this will be straight. So this is theta C and this is L by 2. So therefore this is theta C L by 2, which comes out to be, it is this quantity plus we have already found out what the slope is. The expression for the slope is this into L by 2. So VB is PL cube by 24 EI ZZ plus PL cube by 16 EI ZZ, or VB is 5 PL cube by 48 EI. Just excuse me for a moment. Hello. எடுத்துன்னு போயிருக்கேன், நான் அப்ப கிளாஸ் எடுத்துன்னு இருக்கேன். Yeah, sorry about that. So we have got this as the maximum deflection at the free end. All right. So let us plug the values and find out. So theta A, we know it is 0. Theta B and theta C have the same expression, which is this, which is the question is for 5 kilonewton. So for the question, P is 5 kilonewton. Okay, E is 200 GPa L is 10 meters, I is 200 into 400 cubed by 12 mm power 4. Yeah, that's about what I need. So this is 5e3 into 10e3 whole squared by 8 ei into I. So let us quickly calculate what this is. 8 into 200 E3 into 200 into. So this comes out to be 2.93 into 10 power minus 4 radian. And theta b is also the same. Now coming to the deflection at point C. This is nothing but 5e3 into the length cubed by 24 ei. So this comes out to be Vc. So this comes out to be 0.9765. So hardly 1 mm in the middle. That is because you can imagine it is almost 200 to 400. 200 mm is almost this much. So it is 200 to 400, 200 by 400 mm of solid steel, which is being subjected to 5 kilonewton, which is very less load compared to the section. So which is why we are having the deflection like that. Now Vc, Vb is nothing but this quantity plus this into 5e3, that is L by 2. So this comes out to be 2.2. Just a moment. 200e3 into yeah. So this is 2.44 mm. which if I were to divide it by its length, it is, you can see that it is of the order of 10 power minus 4, the ratio of the deflection at the free end to the length of the actual member, because this is a solid steel section. So I hope this is clear. This is the maximum deflection. This is V at C. And then we have this. So I hope this is clear. Are there any questions at this point about how we did this question? So I take it that that is clear. Okay, so anyway, a steel cantilever beam is subjected to a load at the free end. Now here we are able to see that this is the rectangular section. Now the load is not acting like that or like that. So it is acting at an angle of 30 degrees with the horizontal, with the z axis, so to speak. So, and the load is 3 kilonewton. The section is 250 by 150 and it's a cantilever beam of length 5 meters. So here, although the section is symmetric, that is IYZ, these four quadrants are equal. So the product of inertia, although it is zero, but it will still have unsymmetrical bending because the loading is not symmetrical in this case. So consider the positive YZ axis depicted and let the equation of the neutral axis of the cross section be given as y is equal to some constant into z. Determine the value of that constant is what is asked. That basically what they are asking is, we saw that there will be a line which can represent the neutral axis. So the equation of that line is what they are asking in the YZ plane. So that is what we are supposed to do. Before that, I have this grand expression here. I'll just give a slight flavor of how that came about. But I won't derive it fully now. But when I upload it, maybe I'll add it with the thing. So in the, if this is the XY plane, so here this is positive curvature, and let this be the radius of curvature. This is positive. So in this case, strain in the x direction is given by minus y by ry. This is what we have been seeing. Strain is nothing but curvature into y. So curvature is 1 by r. So that is what I have written. Now this is for bending due to mz, mbz, when the axis is parallel to the z direction. Similarly, if I were to take this as the x plane, now my positive z will be that way. Now my positive z is this way, and we have this as the positive curvature with r z. Let this be the radius of curvature in the other direction. So from here, it will give me minus z by rz as the strain component, and this will be because of Sorry, I think there is some issue with the internet. Just a moment, please. Okay, so this is due to bending moment about z. This is due to bending moment about y. Now, when both of these simultaneously act, then the total strain will be minus minus y by ry minus z by rz. So therefore, the strain sigma x can be written as minus E into Ey by Ry minus Ez by Rz. So this much I have got. That is, I have got the expression of strain as a function of the coordinates x, y, and z in the cross section, provided I know the radii, the radius of curvature in either directions. Now the next this thing would be to evaluate these expressions for radius of curvature. Now balancing moments in, or rather in both directions. So sigma mz equaling 0 and sigma my equaling 0. So if I were to take the section like that, and let us say that I have the stress developed like this, and we have here mbz. So this is like this. This will be my y cross sigma x. This is sigma x. Y cross sigma x added with mbz should be equal to 0 because of equilibrium. So therefore, integrating plus mbz equaling 0. So this will also lead to a moment like this. So that's all right. So this will be simply sigma x y dA integration plus Now I have this expression for sigma x here. So let me substitute this inside the bracket, and then I have minus e y square dA by ry minus e y z dA by rz plus mb z equaling 0. Now you can clearly see why that product of inertia comes in. From where is that quantity coming into the equation? Because we have written the stress as a function of the spatial coordinates, the two spatial coordinates that define the cross section of the beam. Since both the curvatures exist, there will be this will be function of y as well as z. But once we have to balance out the moment in one direction, when we multiply, one clearly becomes izz, the other one will become iyz. So that is where the products of inertia come in into the equations. So this is nothing but, if I take this to the right side, I get ei eizz by ry plus eiYz by rz equals mbz. So this is one of the equations. And this I have got by balancing out the moments along the z direction. Now when I do the same thing along the y direction, it will be, you can work that out. When I post this sheet, I'll post it with the complete derivation. Similarly, eiYz by ry plus eiYy by rz will come out to be minus mby. So this will be coming from the other expression, the balance of moments about the other direction. So we have two equations. What are the unknowns here? These we will only apply. So this we know. E, I, Y, Z, everything is known, because once the cross section is fixed, we know how to calculate the products of inertia. What is unknown are these quantities. Excuse me, I'll just check if the recording is uninterrupted, because yeah, okay. Because this is how I lost the audio in one of the previous sessions, so I just wanted to ensure that. All right, so we have two expressions. So we have two equations and two unknowns. What are the unknowns? Basically, it is curvature in the y direction and curvature in the z direction. So if I were to club these two together, oh, what happened? Just a moment. Yeah. So if I were to club these two together, what do I get? So this is the first expression and this is the second one. So I can recast this as one by Ry, one by Rz equaling MBZ MBY, and this will be EIZZ EIYZ, same thing here, and this will be EIYY. So from here it is just a matter of inverting this matrix, which we can quickly do. So this is nothing but the, the inverse of this into this quantity. Now the inverse of a matrix is 1 by determinant into, it's a 2 by 2 matrix, so these two switch places and these two only change signs. So that is all there is. So let us quickly do that. This is given by 1 by, the determinant is E squared IZZ IYY minus IYZ the whole squared into this quantity will come here. This will come over there, and then this will just be negative of what it was. Into this quantity. So if we multiply this out, MBZ into, or rather I should, anyway, that calculation, because I'm also, I don't want to run completely out of time. So that calculation, one can simplify this, get two expressions for the curvatures, these two curvature, and then substitute it back into our grand equation here, sigma x, and we will be arriving at this equation where sigma x is yizz minus ziyz into mb plus this quantity, entire thing, negative of the entire thing. Now for the question in hand, it simplifies further because IYZ for a rectangular section, IYZ is equal to 0. So therefore we can knock off many terms here. However, if this was an asymmetric section, then IYZ will definitely exist. I suppose in the assignments also the question that has been asked is an angle where IYZ will exist, which is why this bigger expression is what one needs to use. So I just wanted to brief about how that has come. And anyway, when I'll be posting the sheet, I will post it along with the derivation, complete derivation for that. So in this expression, let me take out the terms that are having IYZ. So this term doesn't exist. This term doesn't exist and this doesn't exist. So the expression waters down to this quantity. So this is what sigma x is now. Now Iyy and Iyz we know, we can calculate for the rectangular section. Now we just need to calculate what the bending moments are about z and about y. From this question, we can see that this load can be resolved into two components. So this will be 3 cos 30 and the other component will be 3 sin 30. Now I hope you are able to see that 3 sin 30 is the load that will actually bring about bending moment, that will actually bring about mbz, about z. So this will be about the z axis, and the maximum load, maximum moment will naturally be at the fixed end. So what we need to do, this is the load at the free end, this is the length. So we just need to multiply this in order for us to arrive at the maximum moment at the fixed end. So therefore, the bending moment about the z direction is 3 sin 30 into 5, that is 15 sin 30 kilonewton meter. Similarly, mby is nothing but this will be 3 cos 30 into 5 again, so it will be 15 cos 30 except this will cause, so this will be negative because of the, because when z is positive, this will create a compressive stress. Yeah, and in our derivations, if we see, when z is positive, no, this will also be positive. Fine. All right. So these two we have figured out. It is just a matter of plugging into this in order for us to get sigma x in terms of some constants and two spatial coordinates y and z. So the condition for the neutral axis is that sigma x has to be equal to 0. So we just need to find out the expression and equate it to 0. We will be getting the expression of the neutral plane in terms of y equal to kx, and we can determine k from there. I'll refrain from doing it now. When I post this sheet, I'll do it completely and I'll post. But I'll just discuss about how to solve the other questions in the same problem. The magnitude of the maximum bending compressive stress experienced by the beam is what? Now, in this question, let us apply our same logic that we did earlier, that we are looking at the cross section from the side here. I'm sorry, 1 minute. Yeah, so we are looking at the cross section like this. We have the load applied one of the loads applied like that, and the other loads applied like this. So this creates a bending moment like that, actually speaking, and this one creates a bending moment like this. So we have both moments acting like that. Now, if I were to segregate this into 4 quadrants, this bending moment causes tension here, and compression here. Similarly, this causes tension and compression. So from this, we can clearly see that our neutral axis will be something like this. Once our neutral axis is determined, the equation of which will come as a result of our first question's answer, y equal to some z, which I will post when I do. So once this neutral axis is determined, we can clearly see that the bottom part is in tension, this part is in compression. So the question is asking what is the maximum magnitude of the maximum compressive stress, maximum tensile stress, and what is the deflection at the free end. So once the neutral axis is determined, we know the center of the uh, rectangle is the point of the centroidal plane passing through the centroidal plane, and our neutral axis will pass through that point. In that case, the coordinate of this will be the point which experiences maximum compression. So this point which is y equal to plus h by 2, z equal to minus b by 2, with the understanding that this is b and this is h. Why is z minus? Because we know if this is y, this is z, we are looking at this point, so it goes in the negative y direction, negative z direction, which is why this is the actual coordinate of the point that experiences maximum compression. And just the mirror image of this about the neutral axis will give us the point which experiences maximum tension. So once we have this expression, it is just a matter of plugging in y equal to h by 2 and z equal to minus b by 2, and we will be getting the expression. We will be getting the value of the maximum compressive and tensile stress experienced by the beam. As for the maximum deflection, we know that it's a cantilever beam, so the maximum deflection will occur at the free end. So instead of going by this load, we have resolved this into 2 loads. It is just a matter of superposition of 2 independent cantilevers which are deflecting due to point loads acting at the free end, with the only key difference being for this load, E will be 150 into 250 cubed by 12. For this, it will be 250 into 150 cubed by 12. And we just need to add these in order to vector sum in order to get the actual deflection. So one deflection will be this way, the other will be somewhere that way. So using the vector sum of both, we'll be able to get the final displacement of the free end of the cantilever. So that is the essence behind this question. So in any case, when I post this, I'll solve this completely with the answers vetted out and then post so that you have that at your disposal, because I'm not able to go much longer because my throat is starting to give in. So I'd rather stop here. Are there any questions at this point? Because I've been discussing these things, but if there are any questions now, I'm happy to take them. Is it clear about what we discussed today? Right from some rudiments of unsymmetrical bending to deflection, deriving the deflection using double integration and moment area method, because those are the two that are presently discussed in week 10. We will be seeing more methods about how to use energy and other things in order to evaluate deflections. That will be the topic of next week. But presently, from the topics that we discussed, are there any questions? Are there any doubts? Or do you want me to explain anything that came in the assignments? Is everything clear there? Okay. Okay. Excuse me. All right. So if there are no further questions, perhaps I'll wrap it up with this here. And when I post this sheet, I'll fill in all the answers and post it so that you have it at your disposal. So I'll see you in the on coming Friday. We'll be discussing the contents of week 11, which will have to do with more methods on calculating beam deflections and so on. So till then, I'll take leave then. Thank you for attending.